use it in the same way. You might have problems where objects actually run into the spring. You might have problems where we're jumping onto a trampoline, or anything like that. Would be cases where we're going to talk about elastic potential energy, and then you'll compute the same way we just did with other problems that we looked at. And so we have this thing called elastic potential energy, pretty important thing. And what I usually write that as E with a little EL after it as an elastic potential energy. The equation for this is going to be 1/2 times this letter little k times x squared, where this k represents something we'll refer to as a spring constant. And that basically is a measure of how stiff or loose a spring is. For example, a slinky would have a very low spring constant because they're very wobbly, and the shocks in your car, the springs in your bed would have high spring constants because they're more stiff. Spring constants are related to units of newtons per meter, and it will take this much force to move a spring this many meters per meter. And the x refers to, what does the x refers to? What? Yeah, this is just compressed or stretched. Compressed or stretched. So, like a pinball machine, how far you pull back the little plunger thing to launch the pinball, you'll be storing elastic energy in the spring. Then it pushes the pinball forward, giving it kinetic energy, and then off it goes through everything else. So that is the basic idea of elastic energy. Just make sure, again, one big common mistake is forgetting this squared sign. That's very important for you not to forget. So try not to forget that. Question about elastic potential energy. Pretty simple so far. Oops, not the button on that. So the other thing that we'll look at, and the last kind of thing we discussed, is a kind of a form of energy, but not exactly. And that's a lot of times you'll see referred to as either the thermal energy, internal energy, or, well, sometimes it's called the work done by friction. And there's one worksheet we might do that will refer to it as dissipated energy. All of those, or all of these terms, are the same thing. And they all refer to energy you lose to friction, or if you get warmer during a process. Those are all really the same idea. And we're going to compute them in one of two ways. One way we'll do them sometimes is if you are looking at a question and it asks, usually it will ask for the work done by friction. We'll actually use that same equation for work we already have. We'll just say work equals the force of friction times displacement. Instead of doing just F times as normal F or whatever, we'll do the force of friction times displacement in order to find the amount of work done by friction. And the other way we'll do it, in some cases, if you had a problem where you knew other parts of what was going on, so let's say you got like a car that was traveling at 10 meters per second, and you knew that sometime later the car was traveling or was slowed down by friction, so that was only going 5 meters per second, and you figured out what the kinetic energy over at the beginning was and the kinetic energy at the end was, and you knew that they were going to be different and it's going slower. Then you just subtract those two things, and you then get the work done by friction. That's the other way we'll sometimes compute that. So in one of those equations, it would be like, you know, the initial kinetic energy would equal the final kinetic energy plus the work done by friction. So this second one here isn't like really an equation I'd write in my toolbox or anything, because it's going to change every time. But if you know that your initial energy isn't equaling your final energy, that means whatever is different was probably lost in friction. So you just compute it straight out. That's how we'll find them. But all those terms are the same thing. Thermal, internal work, by friction, dissipated, all mean the same thing. Something's getting warmer as the problem goes on. Any questions about that? Is that making sense? Yeah. So that's exciting. Quick side note here, something I tried to talk about the other day, is this. This happened several times on the final exam. So let's say we had a problem, and you're doing some math maybe in this problem, and you were doing a force kind of thing, and you said you had, so it would be like maybe the applied force plus, and you had mu times M times G for the force of friction equals M times A.
there were several of you that felt that a good choice at this point was to cross off these two m's and try and solve for the applied force. Is that a good decision in life, do you think? No. Not all of those terms have m's in them, so you cannot do that. So that will apply also to our energy work and problem, because there might be cases where not every single term has an m in it, so you can't just cross off the m's that you feel like crossing off. Right. Realistically, this should be divided by m on that side. So just that happened, I don't know, how many times, but enough times in the final where I was getting very frustrated by it. You should know better than that. So don't do that. Okay, questions about that? Yeah? All right. Not all at once, not all at once. Yeah. That's my sarcastic way of saying kind of. So let's do a sample problem then. That'd be pretty awesome. What do you want the problem to involve? Let's play like some problems here. Maybe some more depth. So what should the problem be about? Someone give me an object here. So Mike playing tennis. All right. Good stuff. Now I got me loaded. Okay, so here's Mike. He's pretty tall. Got my tennis racket here. I'm going to hit a tennis ball. Green, yellow, there we go. Hit tennis ball. Tennis ball probably has a mass of like maybe at best not even a half. Let's say it's 10 to the kilogram. He's going to hit the tennis ball. Let's say the racket is basically going to be elastic, right? Because you're going to pull the strings backwards, you're going to fling the ball forward or something to that effect. So it's going to be a little bit of push. We're going to be a little, what do I say there? Anyways, trying to think. So the racket, let's say the racket has a spring constant of, I don't even know what it would be realistically. Let's say 200 newtons per meter. And the racket gets pushed backward, let's say 5-7 meters when it hits the tennis ball. Right? Rackets get bent backwards from the thing forward. So we're going to assume somehow the ball was at rest when the problem started, I guess. And then we want to find the final velocity of the tennis ball. Good stuff? Good stuff. So the final. So that's actually that's probably actually easier than I wanted to do right now. You would just then, so I'll ask you, what would you do in this case then? How would you set that up? Any thoughts? This question even possible. Mike, you want to help us out here? You appear to be sleeping. So I'm not sure.
No, I'm not.
All right, good. Well, why don't you help us out then? How would you find the final velocity of the tennis ball in this case?
Final velocity.
Yeah.
I don't know about the final velocity.
Oh, well, what do you know about it?
That 132 meters per minute. That's
All right, here it is.
my contribution.
Great contribution it was. So what are you going to do with that? Great, so let's do that. So we have 1/2 times, what do you say, 200 newtons per meter times 0.005 meters squared. And so I know what that's going to be. So 0.5 times 200 times 0.005 to the second. Ooh, that's not very big. 0.0025 joule is my elastic energy. So that's not real good for us. But anyway, so now Mike, what would I do?
I have no idea.
Oh, ouch, ouch. Anybody else have a thought? What you're here to find out? Yeah, Ryan. Great. So ultimately, what we're going to do here is we're going to hopefully say something. Oops, sorry. Say something to the effect of that the initial elastic energy from the racket will equal the kinetic energy of the ball at the end. So what we did there is we did half that already. We found the elastic energy, and now we're going to try and see what we can do in terms of finding the final velocity, because we know that the elastic energy and kinetic energy are going to be equal to each other. So I can say that this 0.0025 joules number equals 1/2 times mass times velocity squared. So you can do that stuff. So that would be 0.025 divided by 0.5 divided by, what was the mass of that? 0.1 divided by 0.1 with the square root.
of that number. Not very fast, not this way you do slow. Just kidding. Makes some noise right here. Speed is 0.223 meters per second.
Yeah, it's not fast.
So, I'm taking the fast roll by stuff. So, there is how you set it up. Questions about that? Make sense? Simple enough? Let's see if we can do a little bit harder one this time. Okay, so let's say we had a car on top of a ramp, a hill, if you will, that's going to roll down into some kind of spring at the bottom here. And we want to find out what the spring constant of that spring needs to be. Yeah, I'm hard to improve on this one. What the spring constant is of that spring, we want the spring to need to stop the car within 1.5 meters. So the spring's going to compress 1.5 meters in order to stop the car safely. We want to know what the spring constant needs to be for that to happen. So we have a car up here. How tall is this hill, do you think? Give me a number. 17 meters? Yeah. Compromise, is that one? And then can you get a speed? 134 is a good one. 34 is even better. But we'll go with that. So there is our problem. So let's, first thing I always do in these questions, try to just think to myself conceptually what's going to be present in terms of the energy. So at the top of this hill, what kind of energies are present? Which potential? We have two potentials now. Gravitational potential energy. Is there any other kinds? Kinetic, is the thing also moving? So you have to make sure you ask yourself, really now there's three questions. Is it above the ground, yes or no? Is it moving, yes or no? Is it a spring, yes or no? If the answer is yes, you have that kind of energy. If not, you don't. At the bottom, we have just elastic. And so if you were to set up some math for that, in the bottom, you just have elastic. So if we're setting up an equation, we'd always start with energy initial equals energy final, like that. So you would say something to the effect of energy kinetic at the top plus energy gravitational at the bottom, at the top, equals, we said the spring's going to stop the car. We can assume that there's no EK at the bottom and no EG on the bottom because it's the bottom. But at the bottom, we just have the energy elastic final. What? Oh, yeah. Very good. And so you would plug your numbers in. The other thing in this question, this is a good example of what I said before. If you have 1/2 now, mg squared plus mgh equals 1/2 kx squared. Can I cross off the masses? No, we all agree no, right? There's no mass in this term over here. So this probably would have had to be given a mass in order to finish. This mass might be 150 kilograms. Who knows? It's probably too low, but there you go. There you plug your numbers in. I'm not going to finish it because it's all in the ring, but you now know the mass, the initial velocity, the mass, gravity, height, and the x. You just go through and solve for k. Homework from that backboard over there. But speak about the book. That's 3, 29, 25, 26, 30, and 31.